So it is time. Welcome back from. So I would like to introduce and also welcome Dr. Matipon Tang Matitham, who will be our honored guest speaker for this session. So, and if you are curious all morning about the microwave machine in front of the room, he will be the one telling you all about why we need this machine. Okay, please take it away, Dr. Matipon.
Okay. All right. I welcome you all again. So I think you all probably being pretty tired and sick of Python by now. All right. Of all the programming, all the data analysis. So let's switch gears a little bit. Let's talk about something else. Talk about something different. I know the workshop is like observation, optical astronomy research, right? So Dr. Bright asked me to, let's kick things up a little bit. Let's also talk about what's beyond out there, beyond visible. So obviously, you're all sitting here, you probably know by now, there are other electromagnetic waves beyond the visible spectrum, right? There are other lights that our eyes cannot see. But let's think about it a little bit. What does that mean? If there's something that beyond our eye can see, so how do you know it's there? How do we prove that there are other lights beyond what we can see? Any ideas? Any ideas? Use microwave, but how? How do you prove that it's not there? Okay, if I turn this on, oh, you guys are just honing on this. All right, so I can turn this on and I can see there's no light coming, but it's also something changed. If there's something you can cause some kind of change that is not associated with visible light, that will be approved. Unfortunately, every time microwave turns on, the little lamp also turns on, so you can't do that with microwave. But so what else? How do you prove that there are other ways that we cannot see? There are other lights. That's a good example, right? So I can hit some button that makes something light turned off and on, or I can flick a switch and turn off the monitor. You can't see what's going on from here to there. So there has to be something beyond our eye can see. We don't know if it's electromagnetic wave or something. Maybe it's sound, but we can't hear. But there has to be something. If we can cause something to happen that we cannot see, that will be another way, right? Or if there are something that happened differently from visible light, right? Because obviously, if there is also invisible light that we cannot see, but it does exactly everything visible light does, then that will be pretty hard to prove that it exists, right? So to prove that beyond visible light exists, we need to find something that behaves differently from visible light. And that's what we're going to do today. Okay, so we're all probably have some physics education background, physicists here. What are the other light spectrum beyond the visible? Give me some examples. Oh, come on, you don't go for the microwave? Radio, okay. Microwave, X-ray, what else? Gamma rays, I'm going for a extreme one. What else is there? Ultraviolet, IR, infrared. Okay, so we're gonna try to see if any of these we can make it and let's see if we can demonstrate it. All right, so a little bit. So my background in research, actually, I was a theoretical astrophysicist. I used to study cosmology, but now I'm just doing outreach. And I'll tell you a bit more about outreach that we do later. So part of my job is how to communicate with people. And I think some of you also have to do this also at some point. So maybe something you can do. So let's say you want to demonstrate to people that there is more than what your eye can see. To just focus our astronomical observation. I mean, obviously, if it's your career, you can pick what wavelength you want to study. But as a humanity as a whole, if we just select only the visible spectrum to understand the universe, that would be like trying to see the world through like with black and white, you know, without all the missing color information. So you can learn a lot more about it. I'm gonna try to see what we can do today. So to demonstrate what are the other visible. So I said this, well, this button does something to the I didn't do that. That wasn't me. Okay. But this button, I actually did not do that. Why does it keep happening? I'm pressing the button. I don't know. Okay. So this button, we know that it can do something to that. How do we prove it? Well, if you have your phone, pick up your phone, turn on the camera. Some of your phone will be able to detect this. I'm going to press some buttons and see if you can see the red light in your phone. Somebody can, some will not be able to. All right. Who can see the red light? Raise your hands. Okay. All right. What kind of phone are you using? Is it Samsung? Is it Samsung? Anyone else? Any other phone? Android? Any iPhone user see the red light? No. But wait, what can you see with your naked eyes? No. What's wrong? What's going on here? What's that? What's going on here? So this thing is emitting some kind of light that our phone can see. It causes some change in the phone, but obviously it doesn't, this change doesn't register to our eyes. There you go. That's a proof that there's something beyond visible. So what's going on here? Well, this emits infrared, near infrared. It's basically visible. It's an optical spectrum, an astronomical term, but it is not visible to us. And in fact, all the camera CCDs can detect IR to some extent. But sometimes this causes a problem because if something is really bright in IR is close to red, so anything past to IR will also register as red in your camera. So normally you put a filter to block out the IR, but some camera do not do. So iPhone has a filter, and you have most DSLR has it, so it blocks all the red light, all this wavelength of light. But some phone filter let it passes through. So that's why. So that's something you can demonstrate, but you have to use a particular phone. So anybody see this yet? All right. Well, let's get a bit more extreme, shall we? So I got a beautiful toy over here. Thanks to COVID, now we're all pretty familiar with what this does, right? And so what is this? This is an infrared thermometer. Computer again. There we go. Hey, wave, say hi. Say hi, mom. Okay, so we're seeing something. Sir, why are you wearing sunglasses? It's indoor. What? No, there are sunglasses. What's going on? So we all know, it's easy for us. We all know what's going on here. This is the infrared camera. So this is is another wavelength of the infrared in a different kind of wavelength. That was near infrared, as we would know it, we would call it. And this is more like a far infrared. So this sees and the things that emits far infrared are things that are hot. The more hotter it is, the more it emits. So you can see all the warm part, the bright part. So I didn't want to here because you're close. All right. So why don't you pour some water in the glass over there? And then you mind dipping your finger in the glass and write something on your face with it. And you can see the glass is pitch black because it's cold. So then write something on your forehead with it. Maybe a little bit more water. A little bit, maybe not too much, but that's all right. It's okay. Oh, maybe your neck. Maybe that's because it's hotter. Let's see that. No, doesn't work. Well, it works. Okay, let me try that again. Can I dip in here? Are we double dipping? All right. My arm. See how that registers. That. Oh, come on. I mean, no, I see it. Yeah, there we go. But you can see that's part of it. Right? Whoop. So we just demonstrated this definitely has something to do with heat, right? And you can see the body part that's less protected. The neck is very hot, and your clothes, your shirt is, some part hotter than the others. And you let's look at the ceiling. Wait, what's the dark places over there? That's an AC, right? So AC is cold. So there we go. Now we've seen that it definitely has something to do with heat. Now let's see that, but as I said, to the best way to prove that this thing is different from visible light is to see that it does something differently from visible spectrum. So we're gonna see that something that are transparent in visible might not be transparent in infrared, right? And something that are opaque in invisible might actually be transparent in infrared. So we're gonna try that. So let's see. The idea is let's see if we can block infrared with anything. Let's just do some examples, right? Okay. Hold up your glass to your face. Ooh, the glass is pitch black here. So what's going on? I cannot see the infrared from his face anymore, right? That's because the infrared is blocking the light from him. Now we know, and we can try this too. Okay. You can see the camera, right? But camera cannot see you. Yep. And also another, somebody hold this for me. I can't be a camera. Here's the clip. No. Oh, not. Oh, what's going on there? Yep. Yep. Here we go. So what would be the analog if you were studying some stars? That's something like this. Would not be able to see it. Because sometimes we have to use infrared, like James Webb Telescope, who's peer through the dust cloud that's blocking a lot of interesting star formation going on. So that's anybody else want to try? Let's see if I have anything else infrared. You have any interesting objects you want to try? Let's see what can block infrared. What about a piece of paper? Certificate? Did you have certificate infrared proof? Now, here's something cool. Maybe you can try. Maybe try a thinner paper with that one. Okay. Press your palms against the paper and press really hard. It blocks the infrared, but eventually your hand can warm it up. And you can let go, if you let go of a piece of paper, it's still there a little bit and it fades away. So that's the heat. So that's something cool. You want to try this, you don't, it doesn't have to be this fancy. This thing can cost quite a bit. You want to try this, students? There's a lot of things. So, you know, the remote control, everybody has camera phone nowadays, so that's pretty easy. But also, you can try it maybe with a, you know, nowadays it's probably pretty easy to find one of those handheld thermometer that you check. And you can give an assignment to a student. Let's see if we can sheet the thermometer. If we can put something to block it. What can block it? Can this block it? But why can it block it when you can see through it? So that's something, you know, you can talk about your student with. I'm gonna trip myself. All right. Good so far. Anyone else want to try anything? Do you have any interesting object you would like to try or share? No? You want to try something? No? The what? Banknotes. Maybe it's just cold. We don't know. But let's see. Yeah, but it actually, it blocks the light coming from behind you. So it's, yeah. So that's another one. All right. But that's just infrared. Anything else close to the visible that we can maybe think about? What other wavelengths are there? We talk about. There's infrared. What's on the other side of the spectrum? UV. Okay. Do we know anything that can generate UV? The sun, obviously. Anything else that can generate just the UV? Because if the sun just generate UV, it would be pretty hard to prove if it generate both UV and visible at the same time. Is anything that only generate just only the UV? UV laser, anything else? Oh, I have some over here. How about this? You know what these are? UV lamp. Exactly, UV lamp, or you know, we know it as a black light. So it's emitting UV right now. Can you see it? Trick question. The answer is you can't. You can't see UV. You can see some of the blue light. That's a visible. That's different. But so a lot of this is UV, which we cannot see, right? However, and we don't have a UV camera, as at least not right now, as of yet. But there are something. Let me turn off more lights because it needs to be quite dark in here. The other light switch. Thank you. It came back on. There are something that can absorb UV and release it back in another different wavelength, like these. What about paper? That is and you can also try to see it. And I think I have let's come on and play around a little bit. So I think we've been sitting up. Okay, why don't we all play around? I have the screen lamp here, and of course I do have the IR, and this is I kind of some of these I think is normal, but wait, there's something on there. Why is there mark up there? Two things on there. So it can be a lunar surface. Why you think it's half right? That's not there. So if you shine on regular light, and there's another few things. If you shine on regular light, you go on to flow, but you see the flow is still uniform, right? But if you shine on just UV, it's a little slightly. So this is clearly, so this fluorescent stuff happens to activate on both visible light. Right? So you can tell that. So we have a different material, and you can find from the other material and see if you can find something. It's definitely and I have a and people find something that's not visible, but that only that behaves differently from visible and UV parts. So like in IR, we already found that with that in IR. I wonder, actually, I don't know the answer. But is there anything that is transparent in UV, not invisible? So let's play around with that. I want actually you guys to compare it. So lamp and you want to the IR camera. You wanna stop chicken, see if it has when you can spy on your face? Oh, you know you that's a lot. That's a lot. That's a lot of sunscreen. And this is another really oh, hot glasses. Right. What is your So what we're gonna do? What we can do is so let's see. How about that? Is one of these selected? We'll find out. Let go. Oh, I forgot to do that. These actually they're pretty transparent. Maybe they've lost a different amount of things, like some of them like lots better. But that's something. We can play it with and I looked it up. He actually did that, and he was one of the few people who played. But then he like looked at it so like he's like before he had all the there's lots of probably UV right anyway, why? Anyone buy it? All right. All right. Guys, need more time to know? Oh, bang on. Okay, all right. Yeah, okay. Now, next, we're going to get to the microwave. All right. Then, we need to get back to my. Right. So there are all these lights belong to the same electromagnetic spectrum, but there is something that makes a difference. So what is the quality that determines what kind of electromagnetic spectrum it is? What's the difference between IR and UV invisible? Wavelength, energy, or frequency? Same thing, right? So we can make a demonstration very easily. So can I have a volunteer? Just one. Hold it, and the string. Yep. So this is very easy demonstration. As you know, wave that travels. So like we can measure the wavelength by however long, whatever the distance it takes to complete the cycle. But if it's moving like this, it's pretty hard to measure because it's just keep going. On the other hand, if we can make a standing wave, that would be easier to measure. Now, a standing wave, the wave's going back and forth, but there are some certain fixed point that we force it to stay around, and we can do some interesting thing. Hold on. So this is the middle point. If I just have the middle point, I can force it to become like the node in the middle, and you can see two little squiggly thing. Now, how long is a wavelength in here? If it's just okay, if I struck it so that there's a node in the middle, how long is the wavelength? Is it distant from this hand to that hand? Right? Because remember, in standing wave, only one single how do you call this? One single. Yeah, this is only half a wavelength, right? So from two nodes, the distance between two nodes, not one node to the next, but you have to count from one node to another node and to another one. That will be one wavelength, right? And from the wavelength is okay. You gotta go back now. We all know that you can either describe a wave by its wavelength or by its frequency, right? And so there is a wavelength. We would say that is a lambda, like frequency. Which letter we use? Maybe nu, right? So how are these related for electromagnetic waves? You know that like you can either use one or the other, right? But these are related by a certain number. Anybody know what that number is? Speed of light. So how is that related to speed of light? You multiply that together, you get speed of light, right? Or F if you prefer, doesn't matter. Either way, it's fine. That means if we can find a wavelength and a frequency of a single electromagnetic wave, then we should be able to calculate the speed of light in vacuum, correct? And that's what we're going to do today. We're going to find the speed of light, all right, using microwave. Well, first we're going to need either a frequency or the wavelength. The frequency is easy because I can just read it off the back. It says the frequency is 2,450 megahertz. Right? The rest we have to do is just we need to find the wavelength. How are we going to find the wavelength? Well, as I said before, if a wave is moving, it's going to be really hard. We can somehow make a standing wave. Well, in a microwave, it's the walls are pretty much the constraints, right? So it's going to have a standing wave in there. That's why they have this spinning little thing here, so that your food doesn't only get hot in a certain spot, so it rotates around. Now we can remove this. Then the problem solved. You have a standing wave. Now we have something to detect that is a standing wave. We have something to detect the hot spot, the node, and the antinode. And we're going to do that by making some s'mores, marshmallows. All right. So maybe you can come up again and see it closer. So we're going to lay out some marshmallows. By the way, anybody have them? Okay. So what are we going to need for this is some kind of microwave, a tray, and plate. And you, of course, you remove the revolving part so it doesn't. It's like the standing wave remains still. You kind of spread the marshmallows around, and the hot spot will pop out more, right? Because it gets hotter. And then we're gonna need some utensils as well. We're gonna find out why later. Okay, and let's see if it works. All right. Whoa, it's spinning. Hey, I'm doing something. So I can hear something up here and in here. So you have to listen. Let's try again. Let's try again. Okay. Okay. Up here and here, right? Nothing between. So that's going to be our distance. I'm getting about this will take 7 centimeters. All right. Now will be the time to use the form. Or we want to have some more. We want to try out more. Actually, let's try that. Let's see. Let's wrap it up. Yeah, pop up right here, right here. Right, so that's the middle. How's the distance? Measure the distance between the two empty nodes actually. It's about, I think we get about here. So let's get over that, make it up. Here you go. We're just going to put I advise you to forward, otherwise if you want that one fine. All right, so we have a lambda at about 7 times 10 to the -2 meters, 7 centimeters, and the frequency at about 2000 megahertz. What's megahertz? That's times 10 to the 9, right? 2.450 times 10 to the 6. So add another 3, that's 9, right? Sorry. Okay. So why don't we multiply that together? What do we get? Was that? Oh, good point. We forgot to divide it by half. This is divide times 2, right? Right. So anybody got a calculator? Let's multiply those all together. Okay. Where's my calculator? 2.45 multiplied by 2 multiplied by 7, I get 3.4, and then multiply that by 10 to the 7, 10 to the 8. So I got 3.4 times 10 to the 8 meters per second. Is that pretty good? That's pretty good. That's in about 10-20% errors from what we know. So that's something you can do. We can get your student to measure the speed of light. That would be pretty interesting, wouldn't it? And it's pretty simple too. You can use like a very common household items, and you can see that it works. All right. And so these are some of the things. So okay, we're done with you. Sorry. All right. Okay. So before we wrap up, I got a short minute. So I want to talk a bit. So this is the kind of thing that I've been doing. So as I said, I was a researcher. Now I'm like doing full time. I'm doing outreach, and we have a lot of things going on in Thailand. I've seen that some of you, I met some of you guys yet last night, right, at the observatory. So we saw some of our events. So but I think we have people who still might not understand what we do here. So let me just give a very quick introduction about the work that we do here. And I'm going to say this. This is going to be a pretty bold statement, but if you feel like this is not true, come and correct me. But I think Thailand is probably the first country in the world that takes a top-down approach to astronomy outreach. And I'm going to explain why. So normally, how it's usually done is astronomy outreach is done in the bottoms-up approach. So if you grow up, you either go to like a planetarium, a museum exhibits, or maybe you join some amateur astronomy group. Maybe you join an astronomy club, and you read it on the news, or maybe you learn about it in the school and you become interested, and maybe that's where you got you here. Or maybe some other people who actually a lot more just interested in astronomy as like a hobby got through to these routes. So this will be like a normal way to go. And these things doesn't really have to do anything to each other. Anybody can set up a planetarium and go there. And this is the way it normally works. And I think this is a great model. This is a really effective way to promote. It's bottoms up, and it's organic, it's fluid. Now, also this is a really important part for a fruitful research organization, because the more you have people that understanding, you get inspired by this science, it's the more people understanding about science, how important it is, the more easier job going to be for a research institution. However, when we started Thailand, NRIT was only started 14 years ago. You might not know this, but 14 years ago, none of this exists. And 14 years ago, when I was a kid, I was a kid a lot more older than 14 years ago. But when I was growing up, we didn't really have any museum or planetariums. The world didn't really exist in Thailand. And I didn't know any amateur astronomers. That wasn't a lot. There's still not a lot right now. There's not a lot. The news doesn't really cover science news because it's not a thing people are interested in. And we don't learn about it in school. So none of these exist 14 years ago. So if these exist, you don't have inspired public, you're not going to have a research institution. So when we started NRIT, we realized that if we're going to start a research institution when none of these exist, it's going to be really hard. And somehow it's going to be hard to communicate to people to get them to understand what we do. So we decided we need to take a top-down approach. We're going to need to fill all those 4 main pillars on what normally constitutes an astronomy outreach. And we're going to have to take the role onto ourselves. We're going to temporarily fill that role in the hope that eventually there will be enough to jumpstart the whole system. And that was the goal for our outreach team. And the thing that I will show is some of the activities that we've been doing. And, in order to fill these roles, for infrastructure wise, we have a local planetarium for the public. And we currently have 4 right now. We're going to open one in the next month or so. And we have a lot more coming, planning. And the closest one, obviously, is Princess Serinthorn Astro Park, which some of you were there yet last night to visit. You see, we have a lot of visitors. Again, none of these was here a decade ago. Even like at Princess Astro Park was completed like 5 years ago, I think. Yep. And we have a regional observatories where public can come in and they can enjoy either our exhibitions or the planetarium. It was we also have some open house for our main telescope, 4.4 meters on Dorrington, and we have a public observation, public viewing every Saturday night, apart from this monsoon season, which is unfortunate now. And over the years, we've had over about 10,000 visitors visiting our planetarium. We have 200,000 people our exhibitions. And just last year alone, we have serviced over 465,000, 500,000 people. And this is and you have to keep in mind, like, none of this really exists 2 decades ago. Okay. And to fill the role of the amateur astronomer, we want to create some hands-on experience. So we have a camp like the RIF Youth Camp, where a lot of the kids is their very first exposure to astronomy outreach. So they came to learn, or even astronomy in general. Some of them just like didn't know anything about astronomy. They joined the camp, they learned to start. Some of them find other things, which is okay, but some of them like really find passion in astronomy. And nowadays, we have had over the years, we have had over 4,000 participants in all of our youth camps. And some of them actually like become our staffs now. We have some of the staff who went to the youth camp and now are arranging the camp for the new generations, which is really nice. And because there wasn't a lot of media presence in the science news, so we have to create a lot of content to try to get people. We have to take our upon the role ourselves to publish some news articles, because not a lot of so you were a newspaper 20 years ago, you wouldn't even know who you're going to get a quote on some dark Event Horizon Telescope discovered a new image of black hole. A newspaper article wouldn't even know who to ask. So we need to somehow make sure they know that they can ask us. So we have to publish a lot of those articles. We have to do a bit of social media presence. And over just last year, we've made hundreds of posts, videos online. And our Facebook followers currently is at about 600,000 followers. And that's roughly about 1% of Thai population. Obviously, of course, like some of the accounts might be double, but also there are also a lot of people who might not, who might regularly visit our Facebook but doesn't really press like button. But that's still by far we are among the top government organization in terms of social media presence. But the big parts of us is educator training, because we want to create something that that has an impact in a longer time. We want to somehow make like a pyramid scheme for outreach. We want to create, we want to train someone who can train the others. And that's the goal here. So a lot of our investment goes into our teacher training workshop. And we do a lot of these workshops a year. We have many different levels of workshop to cater different needs for every kind of instructors. And so this is the biggest part of our program over the years. And over the past 14 years, we've actually started teacher training workshop before Narit even founded. But over the years, we have trained almost 10,000 teachers. And we have a network of teachers on a Facebook group. And on top of that, we started handing out Dobsonian telescopes. So we have a program where we gave these out at Dobsonian telescope on loan. So a teacher can apply, and then, they can, if it gets selected, they get a Dobsonian telescope for free. With the only condition is that they have to keep using it, or we can take it back. We haven't done that yet, but we could. So that's a threat that when with this we have personnel armed with the same training and the same equipment, and we can organize a nationwide simultaneous astronomy observation event at like any time we want. And we have done that. And we have so far handed out about 600 telescopes. So we have 600 telescopes scattered around all over Thailand right now from us. And so, as I mentioned in the beginning, so I think as far to my knowledge, we are the first and like maybe the only country right now that does anything this top-down scale. Not to say that this is the best method at any means. As I said, I think we do this because we have to do it this way because of the circumstances that are unique to us. But as time progresses, I'm starting to see that maybe there's a lot more that we've learned here that's not unique to us, that I think a lot of other countries and organizations maybe can learn from our experience that they can share with us. So this brings me to the last slide. So if you notice on your, let me make sure my computer doesn't run out of battery. Okay. You might notice on your name tag, there's a logo ITCA. Might not know what it is, but this is us. Now, which also we are the official international training center in astronomy under the auspices of UNESCO. And the mission of ITCA is basically what we've been doing, what I've just told you. But we have trained all these things, and we think we learned something really interesting from the way we try to transform the status of astronomy outreach in our country. And we'd like to share this with you all. So under ITCA, ITCA, we're hoping that we can do that. And we're gonna do some of the trainings, it's like some of the youth camp that we've done to our kids, and we're gonna invite all the other foreign students. So if you know any high school students who might be interested to join some of these things, we actually have had a similar event in the past, but we have been a little idle in the past, but we're gonna revive and we're gonna revamp the whole thing again. And we're gonna do some of these teacher training workshops that we've done to almost 10,000 of our teachers, to foreign teachers as well. So if you or any other teacher who might be interested, so that screen is blank. Okay, I don't know why. So if you know any of this, please follow us, join us, or sign up for our at least sign up for our mailing list. So we're in the process of the next fiscal year, the next year, we're gonna start to revamp the ITCA. We're gonna be really active, and we're gonna have a lot more interesting workshop and events. Maybe something similar and more of what you see today. So if you're interested, please join our mailing list, and we're gonna send an email as soon as we find out something new we're gonna do. Or you can talk to me, ask me any questions you have. All right. Are there any questions you'd like to ask? You can be asked about this activity or just about our workshop in general. Anything? By the way, our Dobsonian telescope, we have given some of them out to a few countries. I think we have some of them in Laos and in Cambodia. But don't ask me when if you can get that yet. We are more than happy to train you how to use them. But the details on whether we can give them out to you, it's not up to me. Okay. Okay. Any questions? All right. If anything else you'd like to ask, or feel free to drop us email or just follow our mailing list. Okay. All right. Thank you.
So the snack and coffee are ready. So we're gonna break for 10 minutes, and we have the honor to welcome our deputy director, who will be giving the winning team or teams the souvenir medals for the hackathon challenge. And also in closing ceremony, so 10 minutes, have coffee, snack, and come back and be ready to end this workshop with bang.